large language models, LLMs, they're doing some truly incredible things now, aren't they?
Oh, absolutely.
I mean, writing code, explaining really complex ideas, even tackling high-level math problems, things that, frankly, would stump a lot of experts.
Yeah.
But there's this big hurdle, right? The cost. The sheer amount of memory and compute power they need, it often makes them just impractical for a lot of companies, especially if you need to run things on-premise or in those air-gapped secure environments.
That's exactly it. And it leads to this problem sometimes called the missing middle.
Missing middle.
Yeah, so you've got these giant, super powerful, but incredibly expensive models way up here.
Right.
And then down here, you have smaller, edge models. They're efficient, sure, but they often struggle with the tricky multi-step reasoning you need for complex business problems.
So there's a gap.
A big gap. For models that are smart enough for those complex tasks, but still kind of fit onto maybe a single high-end GPU, we're talking maybe 40 to 80 gigs of memory.
Which is a world away from the massive models.
A huge difference in practicality, yeah.
Okay, and that missing middle, well, that's precisely what we're diving into today.
Sounds good.
Our focus is this new model from ServiceNow, Apriel-Nemotron-15B-Thinker. It's a 15 billion parameter model.
Relatively compact in today's terms.
Exactly. So our mission here is to unpack how this model tries to bridge that critical gap. How does it deliver performance that's apparently comparable to much bigger models, but, at a fraction of the cost and the hardware requirements?
And how they achieved that, right? What's the secret sauce?
Precisely. We'll explore the techniques they used and what this could all mean for, well, the future of actually using AI in the real world. Our main source today is the research paper detailing how they built and tested.
Okay.
Right, let's dig in.
Let's do it.
So the headline number, 15 billion parameters, Apriel-Nemotron-15B-Thinker. And the claim is it performs as well as, sometimes even better than, models like O1 Mini, QW-Q32B, Exxon Deep 32B. These are medium-sized state-of-the-art models.
Right? Often in the 30-something billion parameter range.
Yeah, and this new one does it with less than half the memory footprint. Well, it's potentially a game changer for companies actually wanting to deploy this stuff.
It really is. What's so interesting is how it directly attacks that core problem, balancing that sophisticated reasoning ability with the practical limits of deployment.
Like needing it for complex workflows or RA pipeline.
Exactly. Retrieval augmented generation, where it needs to find information and then reason about it to give you an answer.
Yeah.
Tasks like that demand real intelligence.
But without needing a data center full of GPUs.
Precisely. So the big question becomes, how? How did they squeeze that kind of performance out of a, significantly smaller model?
Yeah, that's what I want to know. And it wasn't just a minor adjustment, was it?
No, not at all. The core of their success seems to be this really sophisticated 4-stage training pipeline.
4 stages, okay.
It addresses that fundamental issue. How do you get top-tier performance without, completely breaking the bank on compute costs?
So they engineer their way around the cost problem.
Yeah.
Let's break down these stages then, because this sounds like where the really clever stuff happened.
Right. So stage 1, model upscaling. They didn't start from zero.
Okay.
They took an existing model, Mistral-Nemo-based 2407, which was 12 billion parameters.
Got it.
Now, instead of training a new 15 billion parameter model from scratch, which, as we said, is massively compute intensive, they used something called depth upscaling.
Depth upscaling.
Yeah. Basically, they duplicated some of the existing transformer layers. You can think of those layers as the sort of core processing units in the network. They just made the model deeper by adding more copies of existing layers.
So reusing parts instead of building totally new ones.
Exactly. And the efficiency gain is huge. They estimate it took less than 20% of the compute compared to training a 15B model from the ground up.
Wow, okay. That's a massive saving right there.
Huge.
So after they upscaled it to 15 billion parameters, what then?
Then came the training. They fed this new 15B model about 100 billion tokens of data.
Tokens meaning like words or parts of words?
Yeah, basically units of text. And it was a really diverse mix. Web pages, scientific papers, technical documents, lots of programming code, math problems, a broad diet.
And did it work? Did the upscaling plus this training pay off?
Immediately. They saw significant improvements, especially in mathematical reasoning, writing code, and tasks that need a lot of knowledge, like the GSM-8K math benchmark and the human evil coding test.
So it consistently beat the original 12B model it came from.
Consistently. It really showed that even this efficient upscaling method delivered the benefits of increased scale, particularly for that complex reasoning. Size does matter, it seems.
Okay, stage 1. Efficient upscaling and broad training. What was stage 2?
Stage 2 was continual pre-training, or CPT. And this seems really crucial for getting the model to actually reason more effectively.
How so?
They trained it further, but this time on a more specialized diet of about 70 billion tokens. This mix included things called reasoning traces and chain of thought samples.
Reasoning traces, chain of thought.
Yeah, think of it like showing your work in math class. Instead of just giving the model the question and the final answer, you show it the step-by-step process, the logical deductions to get to the answer.
Ah, so you're teaching it how to think, not just what the answer is.
Precisely. The data focused heavily on areas like math, science, and following complex instructions. It's about embedding the process of reasoning into the model.
And the result of this stage?
This is pretty amazing. They saw improvements of up to 20% on math and coding tasks without using any task-specific label.
Wait, so they didn't feed it correct answers for those specific problems during this stage?
Nope. It learned purely from exposure to the detailed reasoning processes. It figured out how to solve problems better just by seeing how good reasoning works.
That's incredibly efficient learning. It really underlines the power of showing the model the how, not just the what.
Exactly. It makes the model itself a better thinker, fundamentally.
Okay, makes sense. So stage 3, upscaling reasoning training. What's next?
Stage 3. Supervised fine-tuning, or SFT. Here, the goal was to explicitly train the model to generate those intermediate steps, the thinking process, before it gives the final answer.
So reinforcing that show your work idea.
Reinforcing it and making it an explicit output. They collected around 1 million high-quality examples of these reasoning traces, covering things like function calling.
Function calling.
Yeah.
Like the AI triggering an external tool or API.
Exactly. That plus advanced math, coding again, and those or rags dialogues we mentioned, retrieving info and then discussing it.
Okay, 1 million samples is a lot. How did they manage that effectively?
They used a pretty smart technique they call specialized merge.
Specialized merge.
Yeah, they found that if you just threw all these different tasks, math, coding, function calls, into the training mix together, sometimes they'd interfere with each other. Improving one might make another slightly worse.
Negative interference. Okay.
So what they did was train specialized models. One focused more on math, another on function calling, and so on. But critically, they all shared a common core of general data. Then, after training these specialists, they merged them back together.
Clever. So you get the peak performance on each specialized skill, but combined into one model.
Exactly. It let them make the best use of all their data, even if, say, they had way more math examples than function calling examples. And it worked. They saw big gains, like over 7% better on that really hard A-math benchmark, and over 5% better on enterprise function calling tests.
Very neat trick. Okay, that's 3 stages. What's the final piece?
The final stage, stage 4, was reinforcement learning, RL. Specifically using a method called Group Relative Policy Optimization, or GRPO.
Okay, reinforcement learning usually involves rewards, right?
Exactly. This stage was all about making the model more robust and reliable, especially for tricky enterprise use cases. They designed this advanced rule-based reward system.
What kind of rules?
Things like, did the output follow the right structure? Was the answer actually correct? Did it successfully complete the overall task it was given?
So really focusing on dependability and correctness?
Absolutely. And they got quite specific. For math, for instance, they created a data set of 18,000 problems where previous versions of the model had produced both right and wrong answers.
Why?
To specifically train this version to tell the difference, to recognize and prefer the correct reasoning path over the flawed ones it might have generated before.
Learning from its own past mistakes, essentially.
In a way, yes. For following instructions, they used 14,000 complex, verifiable instructions to make sure it really stuck to what the user asked.
No going off script.
Right. And for code, 30,000 Python and JavaScript examples with multiple test cases to check if the generated code actually worked correctly. It's all about building trust for those complex enterprise jobs.
And this lightweight RL approach helped.
Yes, they found it boosted robustness, especially in areas like RAG, function calling, and handling multi-turn conversations like in the MT bench test.
Okay, 4 stages. Upscaling, continual pre-training for reasoning, supervised fine-tuning with specialized merge, and reinforcement learning for robustness. That's quite a journey.
It really is. And the final model, the Apriel-Nemotron-15B-Thinker that people can use, isn't just the output of that final RL stage.
Oh. What is it then?
It's actually a blend. They took different checkpoints, saved versions of the model from both the SFT stage and the GRPO stage, and merged them together.
Merging again, why?
To balance the strengths. Maybe one GRPO run made the model super robust but slightly hurt its math scores. An SFT checkpoint might be brilliant at math but less reliable in conversation.
So by blending, say, 30% of one checkpoint, 30% of another, and 40% of a third.
Exactly. Those were actually the proportions they mentioned for the final model. It lets you fine-tune the trade-off and get the best overall mix of capabilities, math skill from SFT, robustness from GRPO, all in one package.
That's really sophisticated engineering. It's not just training, it's carefully constructing the final product.
Very much so. It's about optimizing for that well-rounded performance needed in the real world.
Okay, so they went through all this effort, 4 stages, clever merging. Did it actually deliver on the promise? How did it perform in tests?
They tested it extensively on a whole suite of benchmarks, covering both enterprise-style tasks and more academic reasoning challenges. And crucially, they did it zero shot.
Meaning the model hadn't seen specific examples for those test tasks beforehand, testing its raw ability.
Exactly. Testing its generalization.
And on the enterprise side, things like coding, function calls, RA, conversations.
It performed really well. Consistently top tier across 7 different enterprise benchmarks. It actually came out #1 on MT Bench for multi-turn conversations and iFeeble for instruction following.
MT Bench top spot is significant, right? Conversations are hard for AI.
Very significant. Maintaining context and coherence over multiple turns is a known challenge. Doing well there suggests it's genuinely useful for chatbots, assistants, that kind of thing. It was also second on coding tests like MBPP and mixed domain evaluations. So yeah, it looks ready for production systems where you need correctness and reliability.
Okay, strong on the enterprise front. What about the more academic, heavy-duty reasoning tasks, advanced math, science, general knowledge?
Here, it also really punched above its weight for a 15B model. It showed strong abilities in advanced math, like on AM and Math 500, and also on expert-level scientific knowledge tests like GPQA Diamond and general understanding like MMLU Pro.
So it can handle complex logic and math quite well.
Definitely. However, they did note one area where it wasn't quite as strong relative to its other abilities, generating Python code that was guaranteed to be correct and executable.
Ah, okay. So strong coder, but maybe needs a bit more oversight for really critical code generation tasks?
That seems like a fair assessment based on their report. Still very capable, but maybe not perfect in that specific domain yet.
Understood. Now, beyond just getting the right answers, you mentioned efficiency earlier. There was something about thinking tokens.
Ah, yes. This is, I think, one of the most compelling findings. Thinking tokens are basically the internal computational steps, the tokens the model processes internally while it's figuring out the answer before it spits anything out.
Sort of the cost of its internal thought process.
Exactly. It's a measure of the computational work it does to reason.
And how did Apriel-Nemotron compare here?
This is the kicker. It used substantially fewer thinking tokens than the larger 32 billion parameter models they compared it against, like QWQ-32B and LGXN1-32B.
Substantially fewer. Across the board.
Across every single academic reasoning task they tested, it was the most efficient model, especially on the simpler logic and arithmetic problems.
Wow, so it's not just cheaper to train because of the upscaling.
It's also cheaper and faster to run in practice. Fewer thinking tokens means lower operational costs day-to-day and potentially faster response times for the user.
That is a huge practical advantage. Lower memory, lower running costs, faster responses, but still getting that high-level reasoning.
That's the combination they were aiming for, and it seems they largely achieved it.
So, wrapping this up then, we've gone deep into Apriel-Nemotron-15B-Thinker, and it really does seem like a significant piece of engineering.
I'd agree.
A model that genuinely seems to bridge that gap we talked about at the start between the giant, costly LLMs and the smaller ones that maybe lack the reasoning power. It offers this blend of advanced thinking and practical efficiency.
That ability to deliver performance close to models twice its size, with roughly half the memory needs, and using significantly fewer thinking tokens internally, that's a powerful combination.
It really is, and it leads to a big question, doesn't it?
Which is?
Well, if you can now get this level of AI performance onto a single high-end GPU or run it effectively in those secure air-gapped environments, What does that unlock?
Right. What new applications suddenly become feasible? What transformations could happen in industries that were previously held back by the sheer cost and infrastructure demands of big AI?
Think about sectors like healthcare, finance, maybe even sensitive government applications, where on-premise or secure deployment is non-negotiable.
Exactly. Does this missing middle model accelerate AI adoption in those critical areas? What possibilities does that open up for you? Listening now, where do you see this kind of efficient power making a difference?
Definitely something to think about. We hope this deep dive has given you a bit of a shortcut to understanding this next step in making powerful AI more practical.
Yeah, it's a fascinating development.